The Doppler effect is sound waves demonstrated through an object. We will be demonstrating this using the violin.
The Doppler effect wave is a mechanical wave, and the sound is carried through the wave without moving any matter. Sound waves have different frequencies, and we will be playing the D string on the violin. The frequency of that string is 293.7.
There will be 3 demonstrations shown to show different perspectives of when the pitch changes and when it doesn't. 1. The source of the sound standing still while a bystander walks by. 2. The source of the sound moving while the bystander stands still. And 3. Both people moving by each other.
Ms. Mary Grace, and me and my partner are going to explain why oobleck dances on a speaker. What's oobleck, you ask? Well, it's a non-Newtonian base, which means that when you apply force to the substance, it takes property of a solid, but when little or no little force is applied, it takes the property of a liquid. The reason that the substance turns into a liquid solid when force is applied and a liquid when force is not applied is because the pressure applied to the substance releases the water from the cornstarch, making it a solid.
Now you would think that the higher the frequency that you would push through the speaker, the more the oobleck would move due to the fact that a high frequency wave has more vibrations per second. But in this case, oobleck reacts to lower frequencies because they cause more motion in the speaker cone, even through the frequency causes less vibrations per second. So in the speaker, you will need a song that has a lot of bass in it. As the bass is pushed through the speaker, the oobleck hardens and stands up on itself, almost like it's dancing.
When are we gonna go?
After this.
After the video.
Brooke, and this is Maddie. For our science project, we made a wave simulator. This simulator simulates a transverse wave. Transverse waves are both electromagnetic and mechanical, but this one is just mechanical. Transverse waves carry energy in a perpendicular motion. There are three properties of waves: amplitude, wavelength, and frequency. The amplitude can be shown from the rest line to the crest and from the rest line to the trough. The duct tape line is the rest line.
The crest and the trough are both combined together to make up a wavelength. The crest is the highest point on the wavelength and the trough is the lowest. So this is a wavelength. The smaller, and when you're looking at this, the smaller the motion means the higher the frequency and the more wavelengths there are. The larger the motion means the lower the frequency there is and the less wavelengths there are.
Today I will be creating a rainbow and I will be explaining how it demonstrates reflection and refraction of light. For this experiment you will need one piece of blank paper, a bowl filled with water, one mirror, and a flashlight. First, place the mirror on one side of the bowl so that half of it is underneath the water. Next, turn off all lights. Then, turn on your flashlight and aim it below the water so it hits the bottom portion of the mirror. You can see the rainbow. Turn the lights back on. What happens is that when the light hits the water, it refracts into the 7 colors of the rainbow. Then it hits off the mirror, and this is reflection of light onto the paper. So this experiment demonstrates refraction and reflection of light. I hope you learned a lot from this experiment. Thank you for watching.
So I'm doing the singing wine glass experiment, and all you need is a wine glass and water. And right now I'm just going to add a little bit of water to my cup. And then all you need to do is make sure you don't have anything dripping on the sides of your cup. And then you get the rim wet with a little bit of water before you start, because it works better if you do it before. And then we're going to try out different measurements of water to see how different the pitches are. And this is like barely in water, and so this is what it'll sound like. One second. Okay, so now we're going to add a little bit more water to it to make it about half full, I guess. And then just repeat the previous steps of getting the rim wet. And then we're going to try out this pitch and see if it's any different. As you can tell, with more water, the pitch is getting lower, so it makes a deeper sound. And we're going to put a little more water in this bowl. And then we're going to fill the wine glass up about to the top. That's good. It's about 3/4. And if you don't have any more water in your bowl, you can just dip it in here and repeat. And when you're done with that, then you'll repeat and try this out again. And it makes the pitch lower as well.
We are demonstrating radio waves through a sports radar that uses waves to detect the speed of a moving object. The waves bounce back once they hit the moving object, and depending on the size of the wave returning, you can tell how fast it went. And it is shown in the video right now.
Ain't it fun living in the real world? Ain't it good?
We tested out several different types of balls to see how fast they went. We used a wiffle ball, red ball, thingamabobber, baseball, and a tennis ball thrown by a Kathy Harp. It hurts! The tennis ball ranged from 20 to 30 miles per hour. The red one wasn't fast enough to be detected like the wiffle ball, and the baseball went 30 to 35 miles per hour. Yeah!
See, it's easy to ignore trouble when you're living in a bubble. So what are you gonna do when the
tested the waves thing-ish. Yeah. Baseball and a tennis ball thrown by
Tie-dyeing shirts with sound waves.
thrown by Kathy Harv. I give up already.
Some of my
I heard she got some chicken. I was like, what?
chicken.
Okay. We